I'm Lucianna Kiffer, and I'm presenting HaPPY-mine, Designing a Mining Reward Function. This is joint work with my advisor, Rajmohan Rajaraman. In this paper, we look at the incentives of mining reward functions as a game where miners are deciding how much hash rate to contribute to optimize their own utilities. So what does this game look like? Well, you have the network of miners with varying mining costs. This can be hardware or electricity costs. And each miner must decide how much hash rate to contribute to optimize their profit. Our goal is to understand the decentralization properties of the equilibria of this game, things like how many miners are participating and the distribution of their hash rates. And we want to design a function that has equilibria with nice decentralization properties. So why do we even need the block reward? Well, we need it to subsidize the costs miner incur to secure the system and also to mint new coins. There are two styles of block rewards. There's the Bitcoin style, where the block reward is halved every 210,000 blocks. So the issuance has this logarithmic curve where the supply is capped at 21 million coins that will ever exist. In between each halving, which is years at a time, the reward acts essentially static. And then the other model we'll call the Ethereum model, or how it was described in its white paper, where the reward is set to 5 ethers forever, so the supply of ethers was uncapped, but it has since increased via multiple forks, but the supply is for now still uncapped. And the main question is, what effect do these models have on the centrality of miners in these systems, and how and if should we decrease the reward, and what's the effect on the issuance? So the plan for this talk is to look at some previous work on desirable properties of mining reward allocation, introduce a new miner game to gain intuition about how much hash rate new miners are incentivized to buy, look at a previous equilibrium analysis of the static reward function, and then the second part of the talk, introduce HaPPY-mine, a new hash-pegged mining reward function, and its analysis. So in an axiomatic approach to block rewards, Chan, Papadimitriou, and Roughgarden, the authors, define desirable properties a reward function should satisfy. They are looking at the time scale of the allocation of a single block to n miners with different hash rates. And they define desirable properties an allocation rule should satisfy as non-negativity, meaning the rewards are not negative, budget balance, where all the reward is allocated, nothing more, nothing less, symmetry, where two miners with equal hash rate will get equal reward, Sybil proofness, meaning you can't split the hash rate and get more reward, and collusion proofness, where you can't join hash rates and individually get more reward. And they prove that the proportional allocation rule is the unique rule that satisfies all of these properties. So more precisely, the proportional allocation rule just means that each miner gets a proportional amount of the reward, where the reward here is constant. And they also present the generalized proportional reward function, which is the unique family of allocation rules that satisfy all of the same properties, except instead of a strong budget balance, it's now a weak budget balance. And that's because instead of the reward being constant, it's now a function of the hash rate of the system. And so it's possible that less than the total reward is allocated. So let's consider a simple game, call it the new miner game. So we have an existing system with total hash rate of 1 and a set block reward of 1. And we want to ask, if a new miner is joining the system, say they have cost C, how much hash rate would they be incentivized to buy? So considering the proportional allocation rule where the reward is constant, miner I will have the utility of their fraction of the reward with, if they input hash rate Q, minus the cost of that hash rate Q. So we get that if their cost is less than 1, meaning their utility is positive, then the utility is maximized at this Q value of a square root of 1 over C minus 1. So the idea we have is that, what if the reward decreases with an increase in the hash rate? Would new miners be incentivized to buy less hash rate when they're joining the system? Again, that's our idea. So we're starting off the same with a system hash rate of 1, but now the block reward is going to start off at 1 and then decrease as new hash rate is added to the system. So we're now in the generalized proportion allocation rule. This is our instantiation of it. And we have that the utility now is this new reward, which is going to be 1 over 1 plus q. 1 plus q is the total hash rate of the system when miner I adds the q hash rate. And so their proportion of the reward minus the cost of that. And we find that the optimal hash rate bought by the new miner to optimize this new utility function is less than that bought under the static reward model. And we ask if we can generalize this. So in the next game, what we have is that now this reward is going down with increase in hash rate, but with this new delta exponent. So potentially more drastically, we'll keep it general. And so we get this new utility function. Again, we're in the generalized proportion allocation rule. This is one instantiation of this function f. And we get this new utility. And what we're able to say is that the optimal hash rate for a new miner decreases with an increase in delta. So a delta of 0 was our static reward function. The reward would just be 1. Linearly decreasing was delta of 1. And now as we increase that delta, we see that the optimal hash rate a new miner buys is decreasing. So this is a potential decentralization technique where this may not affect small miners who don't have the resources to purchase their maximum utility hash rate, but it could help disincentivize rational big miners from joining the system. But what this analysis doesn't do is it doesn't take into account the dynamic game between different miner choices, and that a new miner joining the system may change the behavior of other miners already in the system. So what we really need is an equilibrium analysis. So in Bitcoin Unnatural Oligopoly, Arnosti and Weinberg analyzed the equilibrium of Bitcoin's mining reward function as the simple proportional reward model with heterogeneous mining costs. So we have n miners with varying finite costs. And so a miner I who invests qi hash rate at cost ci qi has reward of proportional to their hash rate, and then the utility is the reward minus the cost of that hash rate. And they find a unique pure equilibrium strategy where they define the C star as the value for which this big X function equals 1. So the C star is a bound for which miners participate at equilibrium, meaning that a miner I will only participate if their cost is less than C star. Otherwise, they will buy 0 hash rate. So let's look at an example of this that they present in their paper. Again, this is their equilibrium. So let's consider n miners, where miner I has cost I over I plus 1. How many miners are going to participate in equilibrium? Well, we have to solve for that big X equation and get that C star is about 0.88. So only the miners with costs less than 0.88 participate at equilibrium. And that C star actually lies between 7/8 and 8/9. So we get that in this example, only the 7 miners are going to participate at equilibrium. So additionally, they showed that the equilibrium of the proportional model is very concentrated. So for example, if you have a miner I participating in mining and another miner J having 20% lower costs than miner I, then miner J must also control 20% of the total hash rate at equilibrium. So the larger the disparity of mining costs, the more concentrated the mining hash rates. So we propose a family of mining reward functions that tries to do better. For the rest of the talk, I'll be focusing on our family of mining reward functions, HaPPY-mine, where the reward is pegged to the system hash rate. This includes our equilibrium analysis for it, how it applies to the example we just went over, as well as general desirable properties we can prove about the equilibria of HaPPY-mine, ending with a discussion of how market value affects our equilibrium and a more general discussion. So HaPPY-mine stands for hash-pegged proportional yield. We are in the generalized proportional allocation family of rules, still talking about miners with asymmetric mining costs, where a miner who invests Q sub I hash rate is going to get a proportional chunk of the reward. This R function I'll describe in a bit, so we define the utility still as the profit, the reward minus the cost, where every function has input Q, which is the value of all of the QIs. So we set the maximum block reward to be 1 and say that as soon as the system hash rate passes some value, big Q, the reward will start to decrease by a factor controlled by the delta parameter. So more precisely, R is the minimum of 1 or the big Q over the hash rate to this delta exponent. So we see here that the sum of the hash rates is less than Q, the reward is going to be, the minimum is going to be the 1, but as soon as the denominator surpasses Q, it's going to start decreasing at a rate determined by that delta we saw earlier. So we can solve for the equilibria values of HaPPY-mine, where for a given delta, big Q, instead of miners with asymmetric costs, and the utility we just defined, we get precise equilibria values. So we define the big X equation as in the oligopoly paper, where C star is still the value where big X is equal to 1, and we define this new value, C dagger, where it's the value such that the big X equation is equal to delta plus 1. And then our equilibria is going to be based on 3 cases, which correspond to 3 possible values of C star and C dagger. And I want to note here that that big X equation is increasing in C, so C star is always less than C dagger. And so these 3 cases will cover all possible values. So let's start with case A. So all the same statements we had on the last slide, and now think of 1 over Q on a number line, and we have that C star is more than it. So if we look at that big X equation again, what that really means is that the miner costs are high. So the equilibria hash rate is going to be low. And we get that this is actually the same equilibria conditions as the Bitcoin oligopoly paper, where the reward is 1, which you can think of as HaPPY-mine with delta equal to 0, since the reward doesn't change. So we have the QI is set the same, with all miners with cost less than C star participating. So C star is our participation threshold. And that the equilibria hash rate, the sum of all of the miners' hash rates at equilibria, this big H, is going to be equal to 1 over C star, which is less than Q. So that's case A. In case B, we have that now 1 over Q lies between C star and C dagger. So again, looking at the big X equation, what we really have is the miner costs are now in the mid-range, so the equilibria hash rate is also going to fall in this mid-range. So what we get is that there is an equilibrium, it does exist, there could be possibly many equilibrium, and we get that all miners with costs less than 1 over Q are going to participate. So now our participation threshold is this 1 over Q. And we're able to define upper and lower bounds for each Q sub I at equilibria. And with those, what we get is that the sum of the hash rates, the big H, is going to be equal to Q at every possible equilibria. So this is case 2, or B. And then case C, the last case we have, is that C dagger is less than 1 over Q. So again, if we look at that big X equation, this happens when the miner costs are low. So the equilibrium hash rate is going to be high, and we get that there is a unique equilibrium this time with a more complicated Q sub I value, but we have that all miners with costs less than C dagger will participate. C dagger is our participation threshold now. And that the sum of the hash rates, this big H, is going to be more than Q. So this is case C. And if we summarize all of these together, what we get is that the overall trend is that the lower the miner costs, the higher the system hash rate at equilibrium, and that there is always an equilibrium, and we can define the participation threshold for each case. So let's see how this equilibrium applies to the same example we saw for the static reward function, where the cost of miner I is I over I plus 1. Let's see how many miners we get participating at equilibria in this case. And we're going to set the delta to be 1, so let's consider the linearly decreasing HaPPY-mine. And let's also set Q equal to 1. So recall that for the static reward case, when we solve for C star, we got that only the first 7 miners are participating. But now for HaPPY-mine, this C star is less than 1 over Q. So we need to check what the value of C dagger is going to be to know which equilibrium case we're going to fall under. So let's input. So it's the input to the function big X where the value is 2. So we can solve for that, and we get that C dagger is about 0.9628, which is again less than 1 over Q, which means that we are in the case 3 of the equilibrium, or case C, which means the first 25 miners have costs less than C dagger, so they're the ones that are going to participate at equilibrium. So we get that our number of miners participating compared to the static case has more than tripled. And we can actually generalize this. So we have that HaPPY-mine with any Q and delta has equilibria with at least as many miners participating as the static reward function. And furthermore, the number of miners participating is actually increasing in the delta parameter. And we can also say that the equilibria hash rate of HaPPY-mine is less than that of the static reward function. And again, we can add to that and say that the equilibrium hash rate of HaPPY-mine is monotonically non-increasing with an increase in delta. So putting those together, we get that HaPPY-mine equilibria has at least as many miners participating with at most the same system hash rate as in the static reward function equilibrium, which is pretty cool. And we saw before that the generalized proportion allocation rule has the properties of Sybil and collusion resistance, which HaPPY-mine inherits since it's an instantiation of it. But these properties are defined at the time scale of a single block, so we ask if the equilibria of HaPPY-mine is also Sybil and collusion proof. So if miners are able to pretend to be a single miner, or if a miner can pretend to be multiple miners, does the equilibrium shift so that they end up with more utility? And we show that they cannot increase their utility. So HaPPY-mine is Sybil and collusion proof. But for collusion, we look at only the homogeneous mining cost case because it's unclear what it means for 2 miners with different costs to collude, like what hash rate at what cost would they buy. So we leave that for future work. And so far, we've been talking about the mining costs and the reward as if they are in the same unit of currency, but in reality, the reward might be in Bitcoin, say, but the cost of your electricity or your hardware is in dollars. So to bridge this gap, we want to understand what happens to the equilibrium when the coin you're mining changes values. So more precisely, consider the equilibrium to be saying that a hash rate of 1 for miner I costs CI units, say dollars, and the reward has 1 unit of worth, so $1. What happens if the currency changes by a factor of R? So 1 unit of currency is now worth R dollars. So if the block reward was worth $1 before, it's now worth, say, $3. So that's our question. So the first result that we get is in the static reward model, which says that the equilibrium is going to shift so that still the same miners are going to participate, but they're going to participate with R times their old hash rate. So the system hash rate is also going to increase linearly in R. And then what we get for HaPPY-mine is that we actually get that the participation threshold increases, so possibly more miners and higher cost miners can now participate. And the hash rate is going to increase by R, so linearly in R until we get to Q, but then it's going to start increasing by a factor of delta plus 1 root of R, which is a sublinear increase in the hash rate. So it keeps to the theme of more miner participation at a lower system hash rate. Right, so to summarize, we've introduced the notion of a mining reward function that's pegged to the system hash rate, that's HaPPY-mine. We show the existence and uniqueness of its equilibria and that it has some nice decentralization properties. But our analysis so far has focused on equilibria, so a natural question is whether we introduce any unfavorable long-term dynamics, which we leave for future work. And this includes miner utility based on the sum of choices over time to capture phenomena like selfish mining and control of supply. And the last point I want to make is that of setting the Q and delta parameters. These are system choices. And where the delta exponent controls how quickly the block reward declines, and the Q is the threshold from which point the reward starts to decline. So setting them is a balancing game which involves a lot of practical considerations, so I'll point to the paper for further discussion on this. And for more details in general, please check out the paper and reach out if you have any more questions.